All right, everybody. Thank you so much for joining us tonight. I would like to introduce Josh Merrill, who will be talking about load balancing in distributed systems. Josh, you may take it away.
Hey, everybody. Thanks for joining. We're going to be giving an overview of load balancing. Before we get started, I just want to thank Single Sprouts for sponsoring this tech talk. So let's get started here. Okay, so quick overview. We're going to start out by talking about load balancing between regions. If we have a distributed system, first we have to choose where we're going to send a client request, which region. And then once we find the region that we're going to use, we're going to take a closer look at how a backend instance gets selected for processing that request within that region. Finally, we're going to wrap up by talking about what a load balancer actually might look like. All right, so this is going to be the demo environment that we use to kind of explain some of these topics for inter-region load balancing. If we have our distributed system here represented as the cloud, we might have multiple regions spread out geographically. And those regions are going to be processing requests that come in from clients also spread around. So the first strategy that we could implement in choosing or selecting a region, it would be latency-based load balancing. And in this case, this will be mostly applicable for services that are going to have like homogeneous requests that look very similar consistently. It's also going to apply to services that really prioritize latency, just getting that request processed and returned to the user as quickly as possible. So how could we make this happen? How could we, what could we use to select the nearest cluster to any given client? One approach would be anycast routing. Now, we have what are called routing protocols, which take routes that are advertised by a service or a source, and they distribute out those routes throughout the network. And then a node within a network will select the route that's closest to it. If it gets the same advertisement from multiple places, it's going to choose the closest to the nearest by source of that route. So what we could do, we could utilize this by saying, if we have a service, in this case, food.com, we could take our internal space that we use for all of our infrastructure. We could essentially advertise the same IP space out all of our exit points in our network. And then from there, the ISP networks that bridge the gap between service networks and client networks would handle the routing in so much that a client would end up being routed to the most nearby entry point for the service network, in this case, food.com. So yeah, another approach for selecting a region to use for processing a request would be variable throughput routing. Now, in this case, we might prefer to use this if we know that we're going to have some requests that are heavier than others. Maybe we have a heavy DB write or a migration that we have to implement. And we know that this is going to take longer to process than some other client requests might. So if we know this, then we can track the current utilization of each of our regions. And then we could selectively route these heavier requests to those regions that are seeing lower levels of traffic currently, so that we can help kind of distribute the load a little bit more evenly. To make this happen, there are a few different approaches. One of them would be variable DNS responses. Now, DNS is the system that helps translate service space like food.com into an actual IP address that client machines can use to send GET requests and other requests. So normally what happens is you've got an authoritative DNS server for your service, and this is going to serve responses, IP responses to requests for spaces that come in from what we call resolvers. Now, these resolvers are essentially just routers that sit at the edge of client networks. Some of them have large networks behind them. Others have small home networks, for example, behind them. So if we were able to determine the size of a network that sits behind a resolver that's making a request for an IP DNS translation, then we could strategically advertise different IP spaces for different clusters depending on current traffic loads. In this case, it would be ideal if we could advertise the cluster B IP space of 2.1 to that larger client network down on the left. And that's exactly what we're going to do. This way, we're going to see cluster B take on that heavier load since it currently has lower utilization in cluster A. This is pretty tricky to implement because DNS is not something that we fully control. We don't control how long resolvers keep resolution response responses in their cache. And we also don't, it can be difficult to intuit how large a network is that sits behind a resolver. We have to take historical data when we see requests come in, and we have to track changes in our traffic patterns coming to our service after we send those responses out, so that in future, if the same resolver makes another request, we can know how large the network is that sits behind it. For some of these reasons and others, we're not going to see this implemented a whole lot, but it is a nice approach, like a first layer of load balancing that we can initialize without even using any of our appliances. Okay, so that gives us a little bit of an idea of how we're going to select a cluster to handle a request, or a region rather. Now let's look at that region a little bit closer and determine which instance is going to handle it on the back end. So a lot of large services are going to see instances between 100 and 1,000 of them that are going to be handling the requests that come in for it. So we have to have a way in which to choose which instance we're going to use. This is going to be handled by something we call front-end proxy, or just a load balancer, and it's going to make that decision for us. And this is what we would prefer it to look like. If we've got our instances over here that are being sent requests by the load balancer, ideally we would have them all seeing similar levels of utilization, rather than some of them getting heavier loads and others seeing less. All right, so let's before we dive in, let's take one final note. It's important to keep in mind that when you have a request coming in from a client, the mapping between that client and the instance that's going to handle the request needs to be consistent. Most services are going to be TCP based, or essentially, conversations that have to maintain the context of prior messages in that conversation in order to do useful things. So if we were to take a client request, the first one that comes in, the first packet, and then we could hash it, and then the resulting hash, we could mod that by the current number of active instances we have. And if we were to do that, we could get a consistent mapping between the request and that instance. And that would mean that all subsequent packets that come in on this connection would go to the same place. This gets complicated, though, when you consider that if you lose an instance in your current pool, one of them drops or hardware failure or something, suddenly that N number, the number of active instances, has changed. And so when you mod the hashes, all the other hashes, connections are going to be dropped because they're going to get sent to different instances. This is a problem. There are some advanced algorithms that handle this for us, meaning that they can give us consistent hashing or mapping, even if you have dynamic N or number of instances. For now, let's just take for granted that we're going to be mapping consistently as we look through these examples. The most simple approach would be round robin. In this case, if we have 3 instances, we're going to see the requests that come in mapped between them, something like this, A through Z, and then we go back to A and through Z again. So this looks quite simple and it's really easy to implement. The downside is that this does not take into consideration the size of the request or the load that it's going to implement onto the instance. So what this also misses is the fact that there might be other services that are sending requests to that same instance. Right now, we're only showing one load balancer. This is just one service. But if other services are using the same resources, the same hardware on that instance, then we could see a lack of balance in how the instances are taking load. And that does, in fact, hold true. This is not something you would see in a production environment because of that. So to step this up a notch, what we could do is implement what we call least loaded round robin. In this case, our load balancer is going to keep track of the number of current active requests on each of the instances that it's balancing between. We have diagrammed here one red or heavy request that's going to take longer to process. Keep an eye on that, and you might see why this still might not be the best approach. If we send that out to the first instance and then a few others to the other instances, you notice that we're updating our number of active requests on each instance. What happens next, though, is we're going to send the next one back at the first instance, and that's going to give it 2. Around the same time, the second instance finishes its request, and it's currently open and available, so we send it the next request. And similarly with that third instance, we send it the next one. What you might be noticing in this really, scaled down example is that there are going to be some requests that end up being queued up behind heavier requests. And because of this, we're going to be seeing a lot of utilization on that first instance and less so on the second and third, especially if you consider this is scaled up to where there are thousands of requests coming in at any given time on the instances. So we still need something better that can actually look at the current hardware utilization on each of the instances. And for that, let's move on to weighted round robin. Now, this approach takes things up another notch in so much that it updates and maintains, the load balancer maintains a health score for each of the instances. Green could be low utilization. And in that case, it's going to send the first request to that instance. It's going to prefer that over the others. Now, when the instance finishes processing a request, it's going to send the response back through the load balancer. And it's in this implementation, it's going to include some information to the load balancer, telling it of its current resource levels, CPU, memory, and so forth. With that information, the load balancer will update the current health score for that instance and use that information to help balance subsequent requests. So one more thing here is we're going to introduce a request coming in from another service. Now, our load balancer here has no information or knowledge of that request coming in, but what we will get is this will be reflected in the response that the instance sends back. In this case, it's sending a yellow response, basically saying, look, I just finished processing one request from you, but I'm actually working on something else right now. So keep that in mind before you send me something else. When that gets back to the load balancer, you'll see that it uses that to update the health score on that instance. Meanwhile, we had sent another request to the second instance, and he just finished, and he's sending a response back that's green, basically saying, I'm done and I don't have anything else to work on, so you can send me more load. And that's exactly what we'll do. We update the health score, send it another request. And one more factor of this implementation is occasionally we'll have instances that haven't seen anything come through in a while. And when that happens, we'll send what's called a trap back to the load balancer. And they're basically just giving it a refreshment of their current state. And the load balancer will use that information to update the health scores and route further requests accordingly. So that's this implementation. This ends up giving us really good balance. This is something that's implemented quite often in production services these days. And it does add a little bit of overhead CPU-wise on the load balancer, keeping track of those health scores. But overall, that's something we're willing to take on in exchange for the better performance. Finally, let's discuss quickly a few implementation mechanisms. So we've actually chosen which instance we want to use for a given request. How are we going to make that happen now? The first approach would be what we call network address translation. This would require our load balancer to keep a table with an entry for every single connection that's ongoing. For every client request coming in, every stream conversation, it has to keep that in the state and essentially open up a new connection from itself to the instance, handling that communication for the client and then routing it back to the client. This does not scale particularly well because it's a lot of load in one place, the load balancer. So we prefer other approaches for the most case. Destination MAC redirection is another option. This doesn't require the same state tracking on the load balancer as NAT, but this is difficult because it requires that we have layer 2 reachability between the load balancer and every instance that it's balancing traffic to. There are some approaches that we can use to get around this, like L2 VPN, where we keep that L2 information in a outer packet, like IP header. But this adds a lot of complexity and overhead, so it's not the best approach. Currently, one of the more common approaches is GRE encapsulation. This is essentially where we take on the load balancer, we take the packet with the client request, and we wrap that in a second IP header. And in that header, we put this destination address of instance that we're sending a request to. Once it gets to the instance, that instance will pop off that outer header, and it will be left with the original header that has the source address for the client that it can send the response directly back to. And this essentially bypasses the load balancer for processing needs. So this is a good approach. It adds a little bit of packet size overhead, but that's fine. And yeah, that's about it. Finally, what does a load balancer look like? Traditionally, they were only rack appliances that you would see in the network racks. F5 is a really common vendor. They're very specialized in how they're designed. They have special network cards that are built for load balancing and nothing else. And they have capabilities like active-active redundancy pairing. The downside is they're really expensive to maintain. They don't scale. You either have the capacity or you don't. So you've seen the industry get away from these more so these days, especially given that we have these cloud appliances now that are easily deployable, integrate easily with parts of larger, cloud ecosystems, and they scale up automatically and they're managed for you essentially. So yeah, this is load balancers, and that's about it. There's a link here to a good paper on one of these cloud appliances that you can read up on if you have interest. But otherwise, that's it. Thanks for the time.
Thank you so much, Josh. What a amazing high-level talk on such a complicated topic. We have time for one really quick question. Yes, Joe.
Yeah, first of all, thank you, Josh, for the amazing tech talk. You mentioned that we can use hashing of requests on the load balancer for keeping mapping consistent. So I guess my question is, what exactly would we hash to make this happen?
Yeah. So you could see some approaches where people might just hash directly on like the packet source IP. More often you'll see used what's called like a 5-tuple, where you would include like the source protocol, source IP and port, as well as the destination IP and port. And that gives us a little bit more of a unique hash that we could then use for scaled up services.
Awesome, thank you.
All right, thank you. If everyone wouldn't mind unmuting to give Josh a really quick round of applause.
All right.
Yeah.
Josh.
Josh.
Good job. But it's great.